We'll now move on to the next talk by Elliot.
What I wanted to talk about here is that some of us have been uh, thinking about how you get to near a hadron collider in a shorter time scale. And I wanted to tell you where we're at and what we think should be done going forward. Um, so, after the European strategy, the preferred option is pretty clear. They've come out with their endorsements for an FCCEE program. But we sort of want to advocate that we don't want to turn out the lights on and just put off the possibility for longer. So this group of us have advocated for going straight to a hadron collider. The main reason for that is that the discovery potential for a hadron collider is really large. And we think that it's also been underestimated as a precision machine. Hadron colliders can, in fact, be quite precise and do a lot of the same EFT operator studies that the E plus E minus program can do. We submitted a document to the European Strategy Group describing this possibility. But of course, we don't have the direct endorsement of the FCC program because they have a particular view of what order things should go in. The main reason this was not really considered in detail by the European Strategy Group, and I believe the main reason was that we simply don't have a well-established cost. The cost is viewed as too high, but also too uncertain. So that's obviously a major issue. And so now that the ESG has supported formally the FCCE program, followed by the HH program, as the CERN flagship, we still believe that it's important to have this as a backup plan, but it also reinforces that program because the Hadron program is part of it. Why should we continue on worrying about cost optimization? Why not just target something for 2075, which is 50 years from now, right? And so some of the reasons that we think this could be very important to keep as a backup option are discoveries that could happen. There are numerous discoveries you could have at the LHC, which would simply not be addressable by an EE program. For example, stop squarks, WINOs at a TeV scale. These things are not directly accessible in the EE program. And you might, these are famous SUSY ones because everybody knows what they are, right? More generally, it's weakly coupled things rather than strongly coupled things that direct production is favored. Another one that could come up is that a Higgsino could be discovered by the indirect detection community. There was a statement in the ESG reports that says that these indirect detection experiments could see a Higgsino at a TeV scale within the first 5 to 10 years of observation, which means we could be facing a situation where we know there's a dark matter candidate at a TeV, but we wouldn't be able to produce it for another 45 years. And so that would be a little sad in my view. And then other things, just to emphasize the breadth of the scenarios, there are many exotic decays of Higgses that are already better at the HLLHC than they will be at FCCEE. Basically, if it's a relatively easy one to find experimentally, there's more Higgses at the Hadron Collider, and it sees them. If they're really hard to reconstruct, then the Hadron Collider might not do as well. So there's other more negative possibilities. Trouble, we all know that the funding situation is far from certain. If there's a really long protracted planning time for this to happen, or there are technical challenges, maybe we want to revisit these questions. And if we don't continue our R&D program or think about how you could do these things earlier, then we won't have that option if it comes time to revisit things. The other slightly more positive view is I also think that the HLLHC is underrepresented in a lot of the physics plots that have been presented, and I'll go into this in a little bit more detail. But it is very possible that HLLHC significantly exceeds its projected performance in some categories, and that might change views of what what the sensitivity gains are from an E plus E minus program. And then, of course, the final one, which is maybe very optimistic, is that technical progress on hadron colliders could make this possible. And I want to emphasize that why is that so important? Why would we switch? Well, both the ESG and P5 have made clear that the ultimate goal is really to get to the so-called 10 TeV part ton center mass. I have a long quote here from the P5. I won't read the whole thing, but it basically argues that getting to 5% on the Higgs self-coupling is really critical to determine the ultimate fate of the universe, and how more exciting do you get than that? Um, and so here's kind of the plot that shows you how to think about these things. Um, and it shows you the HLLHC here, and you don't get that much improvement going to the EE program from the top gray bar. But when you go to the HH program, it's a dramatic shift. You're getting down below 5%. So it's really changing the detail level. And you can say things about matter-antimatter asymmetry and all these things with that kind of precision measurement. It's also the ultimate goal because it gives you much greater reach in terms of stop masses and things like that, and generically top partners. Anything that the stop is a good representative thing for all sorts of top partners which have a naturalness motivation. And you can kind of see this plot from the European strategy where FCCHH is, and a little bit of yellow at the bottom is things you can get from indirect detection, much of which is ruled out by vacuum stability questions. I put a line here where I think that HLLHC will be using the snowmass results from 2022. The European strategy was a little bit more pessimistic on where they would be. We could have a long discussion about that, but let's skip that. Also, minimal dark matter, which is really a hot topic, and we really want to get to this. First of all, it's important to know that despite all the progress we've had in dark matter, both at colliders and direct detection, we have not excluded some of the most basic models, including the so-called the Higgsino model. And so here you can see the top line is these things I mentioned before, the indirect detection experiments that will come on relatively soon, can see way out to quite large masses. And of the colliders, you can see that only the higher energy 10 TeV part ton center mass can actually reach producing them. Improvements in the HLLHC, I just want to first show you on the left side here how much the di-Higgs prospects have changed since we started doing all these predictions. So in 2018, they said they would get a di-Higgs signal strength of 40%. Then it went to closer to 30% in 2022. Now it's at 26%. It may further improve. Some people tell me that. Maybe some of it's too optimistic. We don't know, but it can show you that there really is a potential to increase the sensitivity. At the same time, if you look at the SMEFT predictions for LHC, they're in the very early stages. I would say they are much more immature than di-Higgs was in 2018. There's many channels that are not yet included. Many distributions that have been produced are not included in the fits that are presented in the European strategy and the previous snowmass results. We don't know exactly what's in there because the document that tells you what's in them is not actually out yet. So I can't talk too much about what's in there. But we do know that the LHC will improve significantly beyond what is shown in these plots. And to give you an idea what that means, well, some of them are only a factor of a few away from the LHC being comparable to FCCEE in sensitivity, where some are not that close. Particularly the Higgs fermion couplings, and I'm not sure I understand the detailed underlying physics, are not that close, but the multi-boson couplings and the 4 fermion couplings are quite close. And I could see the LHC becoming comparable. Now switching over to cost, which is, of course, as I mentioned, the main reason that this is not considered as a strategy at this point. And the reason is that here's the cost on the left that's estimated for the European strategy process. And you can see that the cost of the collider after you've built the EE is 19 billion. But if you want to do it standalone, you have to pay for the tunnel and some additional technical infrastructure. And so it's like 28 billion compared to the FCC's EE's 15 billion. So it is significantly more expensive, but it is also much more cost uncertain. And I think this, when I talk to people, there's a real question about where the cost really is. I think we should think about it as a large range, uh, where 28, I'm not sure if it should be one end of the distribution or it should be in the middle. And maybe it could be cheaper. I don't know. I don't think anybody really knows. And so this is the main message of the talk, is that we shouldn't put this R&D on hold for all this time. Um, there's a lot of potential improvements in the cost that were shown at Venice. Um, and so things like improving the supplier base for the conductor. We don't know what the conductor costs, particularly when you buy it in very large quantities. And so that's just estimated. So you'll see at the bottom of this plot um, of the cost. The target price for the long magnets is 2 million Swiss francs, 1 million of which, so 50% of the cost of the magnet is the conductor, but that's a very uncertain cost. In addition, you could reduce the amount of conductor by making hybrid magnets. You could reduce the cryogenic system complexity and cost, and long-term environmental impact by increasing the temperature of operation. Some of these go in somewhat conflict with each other. You can go to 12 TeV magnets, which gives you slightly lower energy. I'll talk about lower energy below, but that requires less conductor and cheaper mechanical assembly and more robust mechanical assembly for the magnets. Also shown in Venice, which I had never seen before, was the ideas of using combined function magnets. I guess there's a deep history of that, but the advantage is that there's less big components and a better filling factor, so you need even less field or higher energy for the same field. So all of these things are there, and I think this is reinforced. I saw a line on Soren Pressman's slides yesterday that said there's significant value engineering that can be performed in these kinds of magnets, and I think that reinforces that. So one important question is, what would we lose if we went down in energy again, right? Because they already went down from the original FCC-HH plan to something more like, so they started at 100 TeV back in 2019. The recent submission was 84 TeV. So I want to talk a little bit about how much you lose, but it's slightly complicated by another thing that I want people to know about, which is that unlike lower energies where we are entirely limited by how much pileup the detectors can handle, as we go to higher energies, synchrotron radiation becomes important. I have sort of a schematic, but reasonably quantitative plot that I put together at the bottom there that shows you there's a pileup limit that doesn't depend on energy. It's basically a description of what we think we can do with detectors. And then there's a synchrotron radiation limit, which scales like 1 over the energy to the 4th power. So 4th power is a big number. These cross at 84 TeV simply because I made the plot using the current number for what the FCC-HH thinks it will do with an 84 TeV machine. That number is set by how fast you can get energy out of a beam screen. And that's itself a major technical challenge and somewhat uncertain. So they've actually reduced their target goal there. It also has a big environmental impact. So if you look at the table, the SR power for the 84 TeV machine is 1.2 megawatts per beam. But for 100 TeV, you get up to 2.6 megawatts per beam, which is apparently a little bit beyond what people actually think is currently viewed as a reasonable goal. And they also estimated a 120 TeV machine. And at that point, you have to start dialing down the luminosity. So what does it matter if you dial down the luminosity? Well, if you look at the right plot here, you can see on the vertical axis is how much your sensitivity changes to a particular parton center of mass as a function of the sensitivity, what mass scale you're interested in, because different processes will land at different places on here. And I do this all as a ratio to the 84 TeV, the nominal FCC-HH machine. And so you can see that if going from the purple line to 0, you're losing order 10 to 15% of your energy sensitivity going from 100 TeV to 84 TeV. But again, this is not a really fair comparison because that 100 TeV machine is making way more synchrotron radiation that may or may not actually be feasible. Now, if you think about going from the 84 TeV machine to a 72 TeV machine, but you now scale up the luminosity because you don't have a synchrotron radiation band that's as strong anymore, and you do some luminosity leveling, you get a higher luminosity. This is from this table from Frank Zimmerman. What you find is that below 3 TeV, the 72 TeV machine is actually better. It produces more. Above order 3 TeV, it starts to become worse, but it's not a very rapid fall off until you really get to the end point. Okay. So then on the timeline, there was a timeline presented for the FCC project to go straight to hadrons from the FCC team. I'm not really qualified to comment on it. This is their more pessimistic one. They had an even more optimistic one, but they say mid 2055 kind of range for turn on. Okay, so to the conclusions. So FCC has been endorsed by the European strategy and should be supported well. I don't disagree with that, but I do think that we should plan for eventualities. There can be trouble, there can be progress, there can be discoveries, and I think the US should maintain an effort to better understand the costs and feasibilities of hadron colliders in what I call the near term, not just putting off to 2075 so that we focus on a few long-term developments. I think we should have an actual cost-optimized solution. In addition to keeping that door open, I think it also strengthens the FCC program overall, because any questions about the long-term feasibility of the Hadron Collider could come into whether we want to dig a giant tunnel. Okay.
Thanks very much, Elliot, for that talk. There's one question or remark in the live chat from Heidi, which says, just to clarify for non-CERN people, this proposal is to build a less expensive but full-scale FCC-HH, in other words, including the large ring, but with less aggressive magnet technology?
Yeah, that's right. It's basically, I mean, already they backed off on the magnet technology a little bit because they were really at extreme when they talked about 100 TeV. And it said, there are various cost optimizations that can be done that haven't been explored, and we just don't have a very firm idea what the cost is. So, double the cost might be triple the cost, or it might be 50% of the more cost. And I don't think we know. I've spent, I'm not a super expert on this, but I spent a lot of time asking various experts, and I've got wildly different answers on it, with the result that I think the answer is we don't know.
Are there any other questions from the community? Anything in the chat or any raised hands? I don't see anything, so I'll thank you, Elliot, and